All right, so buckle up, everybody, because today we are diving deep into Stable Diffusion,
Ooh, fun.
which, if you've been on the internet at all lately, you've probably seen some of the crazy images this thing can pump out.
Yeah, it's pretty wild what it can do.
I mean, it's really shaking things up.
It is.
And we were lucky enough to get our hands on a lecture transcript from a college course
Nice.
where this professor walks his students through how Stable Diffusion works.
Where you at?
And, like, even how to code one.
Oh, wow, that's awesome.
Yeah. So, I mean, are you ready to get your mind blown? Because the secret ingredient here,
What is it?
it's noise.
Noise.
Yeah, like the static on your old TV screen.
Hmm.
It's wild.
I mean, I've seen some of the stuff that Stable Diffusion can create, but I have no idea how noise plays into any of that.
Yeah. So
That's pretty mind-blowing.
this professor, he kind of lays it out in a way that's like surprisingly easy to follow.
I like that.
Yeah.
Approachable.
Yeah, that's
Yeah.
good. So get this. The first thing Stable Diffusion does is it takes an image and starts adding noise to it.
What?
Yeah, and it's not like a little sprinkle of noise. It's like step by step.
Yeah.
It just keeps adding more and more noise until the image is completely gone, like pure chaos.
Yeah.
You know,
So how does it make an image if it's just adding noise?
that's the genius part. The AI is actually learning to reverse that process.
Whoa.
Yeah, so it's learning to pull a clear image out of that pure randomness.
Like denoising.
Exactly, denoising.
Okay.
So the professor, he uses the simple graph to show like a single pixel's value
Okay.
and how it gets all noisy over time, and then how the AI reverses that and brings it back to its original state.
So it's basically learning how to uncorrupt an image.
Yeah, and I don't know, like, have you ever tried to draw something and you start with like a really messy sketch?
Oh, yeah, all the time.
And then as you refine it, it starts to become clearer and clearer.
Yeah, you're like, oh, there it is.
It's like that, but on a whole other level.
That's a really good way to visualize it.
Yeah, so one of the students in the lecture, he asks this question that I think everyone is wondering.
Okay.
He's like, why even bother with all this noise in the first place?
Yeah, isn't the goal to make clear images?
Right. You'd think so.
Yeah.
But the professor explains that by learning to denoise,
Okay.
the AI is actually learning the underlying patterns of real images.
Oh, interesting.
Like it's learning the rules of the game.
So it's not just randomly generating pixels. It's like
Oh,
it understands what makes a realistic image.
exactly.
Right.
And this is where Stable Diffusion really starts to outshine the older AI image generators like GANs.
Jan's generative adversarial networks.
Yeah, those just started with noise and kind of hoped for the best.
Yeah, they were kind of like throwing spaghetti at the wall and seeing what stuck.
Uh-huh. Yeah. But Stable Diffusion is more like, I'm gonna teach you how to make a gourmet meal, starting with just the raw ingredients.
I like that analogy.
Yeah, so it's like it's not just randomly generating pixels, it's actually learning like the grammar of images.
The grammar of images.
Yeah, but then you gotta think about it, right? We're
Yeah.
talking about these huge high-res images.
Right.
That's a ton of data even for a supercomputer to handle.
Right.
So how do they make it work?
Yeah, how do they crunch all that?
So they use this really clever trick.
Okay.
It's called latent space.
Latent space.
Yeah, imagine taking a huge image file,
Okay.
like a giant high-res photo,
Hmm.
and compressing it down into a tiny little JPEG.
Okay.
You lose some detail,
Yeah.
but the essence of the image is still there.
Right. And the file size is way smaller.
Exactly. So they're basically doing that with the images before they even feed them to the AI.
Oh, so it's not working with the full resolution image, just a simplified version.
Exactly. And this is where it gets kind of trippy.
Oh, boy.
Because the professor was saying that this actually mirrors how our own brains work.
What?
Yeah, we don't remember every single detail of what we see, right?
No, just the important stuff.
Yeah, we extract like the key patterns and features.
Huh. That's
Isn't
fascinating.
that wild?
It is.
So the AI component that handles this whole compression and decompression thing, it's called the variational autoencoder.
Variational autoencoder.
It's a mouthful.
It is.
But it's basically the unsung hero of Stable Diffusion.
Yeah, so we've got our noisy image in this compressed latent space.
Right.
But how does it know what kind of image to create from all that noise?
That's the question.
Yeah, it can't just be random, right?
Well, that's where this idea of conditionality comes in.
Conditionality.
Yeah, in the professor's example, he was training the AI to generate specific digits.
Okay, like the number 7.
Exactly. So by giving the AI that digit as input, it's making the whole image generation process conditional.
Oh, so it's not just creating any random image.
No.
It's trying to create a 7 out of all that noise.
Exactly.
Okay, I'm starting to see how this works, but How does it even understand what a 7 is?
Well, it all comes down to vectors.
Vectors.
Yeah, you know how deep learning relies on representing everything as vectors, basically like strings of numbers?
Right.
That digit, the 7, it's actually converted into a vector that the AI can understand.
Oh, wow.
Yeah, so it's like connecting numbers to images through these vectors.
That's pretty wild.
Yeah, and what if we gave it something more complex?
Like what?
Like a whole sentence.
Whole sentence.
Could we generate images from text that way?
That would be insane.
Right. The professor kind of hints at that later on. He talks about using text prompts as vectors.
So theoretically,
Yeah.
we could feed the AI like song lyrics,
Yeah, poems.
even an entire story.
And see what kind of crazy images it spits out.
The possibilities are endless.
Right.
Okay, so now I'm really starting to get how powerful this thing is.
Yeah, but wait, there's more.
Oh, no.
This professor, he gives his students a challenge.
Okay, what is it?
He tells them to build their own stable diffusion models
From scratch.
from scratch
Whoa,
and train them on their own data sets.
that's intense.
Yeah, and remember his example was based on MNIST, which is like 60,000 black and white
Like
images.
handwritten digits, yeah.
Imagine doing that with color images.
Oh my God.
Or a data set thousands of times larger.
That's a whole other level.
Yeah, and these students, they're probably just working with like a single GPU each.
Right.
It's like trying to bake a wedding cake in a toaster oven.
Uh-huh. Good luck with that.
But even if we can't all build the next daily,
Yeah.
in our basements, just understanding how it works is super valuable.
Absolutely.
Like demystifying this technology, I think it's the first step to understanding its power and its potential impact.
For sure, because this is going to change a lot of things.
Yeah, it's a game changer.
It is.
All right, well, that's it for this part of our Stable Diffusion deep dive, but we're just getting started.
But there's more.
Yeah, we're going to get into the nitty-gritty of the code in the next part.
I can't wait.
Stay tuned.
All right. Welcome back to our Stable Diffusion deep dive.
Okay, so last time we were talking about like the big picture, right?
The concepts, yeah.
The concepts, yeah.
The magic behind it all.
The magic. Yeah. But now I think it's time to get our hands a little dirty.
Let's do it.
Yeah, let's actually look at some of the code that the professor shared with his students.
All right, let's crack it open.
So I took a peek, and I gotta say, it's a lot to take in.
Yeah, it's not exactly light reading.
No, it's not like, reading a novel.
Oh,
It's
God.
dense.
It is.
But the first thing that jumped out at me was all these libraries he's importing, like PyTorch and TorchVision.
Yeah, those are like the essentials for deep learning.
Okay.
PyTorch gives you the framework for building these neural networks, and then TorchVision has all these pre-built functions for handling images.
So it's like getting all your tools and ingredients ready before you start cooking.
Exactly.
That makes sense.
Yeah, and the professor really emphasized that his students had to figure out how to load their own data sets for this project.
Oh, that's interesting because he was using MNIST, right?
Yeah, the handwritten digits.
Which is already like all neatly organized and ready to go.
It's very convenient.
Yeah, it's like learning to cook with pre-chopped veggies from the grocery store.
Right.
But in the real world, data is messy.
Oh, yeah, it's more like starting with a whole garden.
Right, you got to do all the prep work yourself.
Yeah, clean it, chop it.
So the students have to find their own images, figure out how to organize them, and then like feed them to the AI.
Exactly. They might be scraping images from the web, using existing databases, or even taking their own photos.
Oh, wow, that's a lot of work.
It is. But once they have their data, they need a way to get it into the AI's system.
Okay, and that's where the data loader comes in.
You got to think of it like a pipeline that feeds the images to the AI.
Okay, so it makes sure the AI gets a steady stream of images to learn from.
Right, and it keeps it from getting overwhelmed.
Okay, that makes sense.
But it's not just dumping images into the AI.
No.
They need to be in the right format, the right size, all that good stuff.
Right, so it's like prepping the ingredients, making sure everything is uniform.
Yeah, that's where those transforms come in that we mentioned earlier.
Ah, okay, so the transforms are like little functions that tweak the images.
Exactly. Resizing them, converting to grayscale, normalizing pixel values, all these little things to make sure the images are consistent.
So it's all about consistency.
Consistency is key.
All right, so data loaded, prepped, ready to go.
Time for the main course.
Yeah, now we get to the real magic, right? The diffusion process itself.
The heart of the beast.
But looking at the code, it seems like it's a lot more complicated than those simple graphs we were looking at before. The ones that showed the pixel getting noisier.
Yeah, those were just to illustrate the basic concept.
Right.
The real deal has all these different moving parts working together.
Okay, so break it down for me. What are the key players in this diffusion orchestra?
Well, first up, we've got the variational autoencoder, the VAE.
The VAE,
the
right?
one in charge of compressing the image into that latent space.
Okay, so it's like taking a huge image and turning it into a smaller, more compact version.
Exactly, like a zip file for images.
I like
It
that.
has two parts.
Oh.
The encoder, which compresses the image,
Mm-hmm.
and the decoder, which reconstructs it.
All right, so we zip up the image, shrink it down, and then what?
Then the forward diffusion process kicks in.
Okay.
We start adding noise to that compressed representation.
So we're blurring it out.
Yeah, gradually turning it into a mess using something called Gaussian noise.
Gaussian noise. Is that like a specific kind of noise?
Yeah, it's a type of noise that's statistically well-behaved.
Okay, well-behaved noise. I like it.
But the point is we're making the image worse.
Right, and the AI has to figure out how to reverse that.
Exactly, but it doesn't do it blindly.
No.
It relies on a key component called the noise predictor.
The noise predictor? Okay, we haven't met this guy yet.
Think of it as a detective analyzing the blurry image and saying, aha, I think this much noise was added at this particular step.
So it's like a reverse engineer for noise.
Exactly. It's trying to undo the blurring step by step.
Okay, I'm starting to see how the pieces fit together, but what kind of neural network are we talking about here? I remember the professor mentioned something called a UNet.
Yes, the UNet is a special type of convolutional neural network.
Convolution, those are the ones that use filters to find patterns in images, right?
They're like specialized lenses that can see the fine details even when the image is buried in noise.
So the UNet is like the AI's noise filtering goggles,
I like that.
helping it see through the blur.
And the professor mentioned that this UNet is even more powerful because it's enhanced with something called residual neural networks, or ResNets.
ResNets. Okay, I've heard that term, but I don't really know what it means.
They're basically a way to build deeper neural networks without running into problems.
Okay.
They use these shortcuts called skip connections that help information flow more easily through the network.
So it's like adding express lanes to a highway to prevent traffic jams.
Exactly. ResNets help the UNet learn more efficiently.
Which is important when you're dealing with something as complex as image generation.
Absolutely. And all this is happening in the compressed latent space from
Wait, so it's like a carefully choreographed dance between all these different neural networks.
It is. We have the VAE compressing the image, the forward diffusion adding the noise, and the UNet powered by ResNets working to predict and remove that noise.
It's amazing how much is going on behind the scenes to make this work.
It is. And remember that question from the student about how the AI knows what to create.
Yeah, how does it know what to make?
That's where conditionality comes in.
Right, the professor's example was generating those specific digits.
Yeah, and he did that by feeding the digit, like the number 7, as an input to the model.
Right, and that made it conditional, but how does it even understand what a 7 is?
Everything in a neural network boils down to vectors, those strings of numbers.
Right.
So that digit, the 7, is actually converted into a vector.
So it's like translating the symbol 7 into a language the AI can understand.
Exactly. And then that vector can be combined with the latent representation of the image. So the AI is working with a combined vector that says, make this look like a 7.
It's like giving the AI a target to aim for.
Exactly.
But what if we wanted to give it more complex instructions? Could we use text prompts instead of just digits?
The professor hinted at that possibility.
Really?
It gets a lot more complicated because you have to figure out how to convert whole sentences into vectors.
Right.
But the underlying principle is the same.
So theoretically, we could feed the AI song lyrics, poems, even entire stories.
And it could use that information to guide the image generation process.
That's mind-blowing.
It is. But before we get too carried away with the possibilities, let's get back to the fundamentals.
Okay.
All of this magic relies on the training process. That's where the AI really learns how to turn noise into masterpieces.
All right, let's head back to boot camp and see how they whipped this AI into shape. Okay, so we've made it to the final stage of our Stable Diffusion deep dive. We've talked about the concepts, the architecture.
The nuts and bolts.
Yeah, the nuts and bolts. But now it's time to see where the rubber meets the road. The training process.
The AI's boot camp.
Haha, yeah, exactly. Like watching it go through art school, learning to create masterpieces by wrestling with static.
That's a great analogy.
So walk me through what's actually happening when we're training this AI.
Well, remember those M-nice digits the professor was using?
The black and white handwritten numbers.
Right, let's start there. We take a batch of those images,
Okay.
and we compress them using the VAE.
So we're shrinking them down into that latent space representation.
Exactly, and then we start the forward diffusion process, adding that Gaussian noise step by step, turning those crisp digits into a blurry mess.
And the AI is just watching this happen. What's it learning from all that?
Well, as we're adding the noise at each step, We're keeping track of exactly how much noise is being added.
Okay, why is that important? It seems like we're just making the images worse.
That information is crucial for training the noise predictor.
Oh, the unit.
Right, the unit, we're essentially giving it a snapshot of the noising process at each step, saying, okay, look at this noisy image and tell me how much noise was added at this point.
So it's like training a detective to look at a blurry photo and figure out what the original image was.
Exactly, but here's the thing. Since we're the ones adding the noise, we already know the answer.
Oh, okay.
We can compare the UNet's prediction to the actual amount of noise we added. The difference between those two is what we call the loss.
So the bigger the difference, the worse the unit is doing.
Exactly. Our goal during training is to minimize that loss.
So we want the UNet to be as accurate as possible.
At predicting the noise, yeah.
So we want it to be like a super sleuth.
A noise detective extraordinaire.
Uh-huh. I like that. But how do we actually do that?
Well, we use this technique called backpropagation.
Backpropagation.
It's a way of adjusting the weights of the neural network
Or weights.
based on how well it's doing.
Okay.
If the UNet makes a big mistake, we adjust the weights more drastically.
So it's like giving it feedback saying, hey, you messed up here, let's try this instead.
Exactly. And we do this over and over,
Okay.
feeding it batches of images, adding noise using backpropagation, and gradually the UNet gets better and better.
So the more it practices, the more accurate it becomes?
Then the loss goes down.
Okay, but I'm still a bit confused.
Okay.
We spent all this time adding noise to images, but the whole point is to generate clear images. How does that even work?
That's the beauty of this whole approach.
Okay.
By learning to predict and remove noise so accurately, the UNet has actually learned the underlying structure of real images.
So it's like learning to paint by first becoming a master at erasing?
I love that analogy.
Uh-huh.
So once we have this well-trained UNet,
Okay.
we can use it to generate brand new images, starting from pure noise.
So we basically just give it a bunch of random static and say, go be creative.
Pretty much we start with pure noise in the latent space,
Okay.
and then we use our trained UNet to denoise it step by step, guiding it with whatever condition we want, a specific digit, a text prompt, anything.
So the UNet is like an artist shaping that noise into something beautiful.
Exactly. And because it's learned so much about images during training,
Yeah.
it can create incredibly realistic images from seemingly nothing.
This is just blowing my mind.
It is pretty wild.
We started with this simple idea of adding and removing noise, and now we have an AI that can create photorealistic images from scratch.
The power of deep learning.
I know, it's incredible.
It is.
Well, I think we've officially reached the bottom of this deep dive.
We made it.
We went from that single noisy pixel all the way to training an AI to generate amazing images.
And honestly, I'm in awe of the whole process.
Isn't that right, too? It's just amazing what humans can create.
And the crazy thing is, this is just the beginning. Who knows what incredible things AI will be able to do in the future.
Yeah, and if you're one of our listeners who's inspired to create the next breakthrough in AI art,
We salute you.
until next time, keep diving deep.